Actually, can you? I'll just ask the team to check. Can you check? I think there's something wrong. Like I can see on the YouTube that the live stream has ended. Can you have? Uh, can you see? Can anybody please confirm if I'm audible and visible on the chat? Can anybody please confirm if I'm audible and visible in the chat? Yeah. Okay. Okay. Cool. So yeah. I'll just begin. All right. All right. Great. So I'll just begin. So the agenda for the today's class is going to be discussing in brief about breadth-first search, and we'll also discuss a couple of problems. And so before we actually begin, I think I'm not sure. I think that there was some issue with the link, and the stream is actually on a different link than it was supposed to be on. I'm not sure, but let's wait for a couple of minutes for some more people to join. And in the meantime, let me just walk you through, guys, through all to what this platform is that we are going to that CodeChef and Unacademy has just launched, right? So before that, let's start with my introduction. So my name is Pulkit Chhabra. You guys may know me as Coder Pulkit C. This is the username that I use on various online coding platforms like Codeforces, CodeChef, and so on and so forth. All right. So I'm a final year student at Delhi Technological University, and I have some experience with competitive programming. I've been doing it for I think 2.5 years now, and regarding some industrial experience, I have worked with Coordination and HackerRank in the past. I'm a 6 star on CodeChef. I'm a master on Codeforces, and I think enough about myself. So let's just move on to the next slide now. All right. So regarding this platform wherein you can come and learn competitive programming, let's just discuss that what are the things that you are going to get. So there will be live interactive classes just like this one, right? And there will be doubt solving, wherein there will be teaching assistants who will help you guys with your doubts during the live class as well as after the class on the CodeChef platform, doubt forum. And also there is a Discord server that has been made. There also people can ask doubts. And the third thing is that you guys will be getting practice problems relevant to each and every course that is there. There will be that will Each course will have a separate contest of its own. I'll just show you in a couple of minutes. And yeah, so the practice can be done there. All right. So, coming to the next point, which is educators, I believe that for any learning platform, educators are the essence of it. Educators are one of the most important, aspects that the person decides upon, that whether I have to buy this thing or not. So, I think, in my honest opinion, not just because I'm associated with an academy and CodeChef, and in general as well, when I came to know that there is something that they're planning, and these are the list of educators. I was really excited to be working with them. So most of all of the educators have a really strong background with competitive programming, and I believe that being just good in competitive programming is not something which is enough to be a good teacher, right? So they've kind of made sure that the educators do have an experience in teaching as well. So yeah, the educators are many of them are ICPC world finalists, IOA medalists, and having good ratings on Codeforces and CodeChef, etc. And many of them, not exactly many, most of them, to be honest, out of all the educators, it's me and there is another educator who is Nishche. We two studying college yet. All of the other educators are actually, you know uh, uh, other educators are working in the companies, in different companies, like Google, Facebook, and so on and so forth. All right. So yeah, I think enough about educators. You can have a list, have a look at the list of educators that is being visible, that is visible on the screen right now. So there's Deepak, there's Himanshu, there's Arjun, Triveni, Tanuj. All of these have been to ICPC World Finalists, or ICPC World Finals, or have been shortlisted for World Finals. Tanuj has been to World Finals twice. There's Murugappan. He is a software engineer at Google, and these are his highest ratings on Codeforces and CodeChef. There's Ria and Sanket. Uh, they have they have a lot of experience in teaching. I know them personally. They are very good teachers. And there's Nishchay and me. Nishchay here has very impressive profiles on CodeChef and Codeforces. He's a 7-star on CodeChef and international grandmaster on Codeforces, which according to me is a big deal. And I think there are just less than 5 people in India with who have touched this mark. All right. So the topic wise structure for the courses looks like this for now. I think this list is also a little outdated. There the couple of more courses have also been added to it. So these are sort of the courses that are available on the platform right now, but more are being added continuously. And in the end you can sort of assume that there will be all those courses which are required to be a competitive programmer, uh, you know on a very good level. So so these are some of the courses and their start dates. When did they start? So greedy algorithms, I took graphs 1 and it started on 21st, and number theory and recursion and DP, sorting and searching, it would cover binary search. STL in C++, basic data structures. This is a whole course which covers many of the data structures and square root decomposition. And this is a beginner level course for those who have not sort of uh, done any competitive programming as of now. All right. So, like I said, regarding the teaching assistants support, so yeah, this is our doubt forum. The Discord servers slide has not been included in the presentation. I'm sorry for that. There's also Discord server wherein there is a channel for each different. There is a different channel for each different course. So I think that will be a much better platform to ask doubts. So that is also there wherein you can interact with the educators and the TAs and so on and so on. Right. So like I said, there will be a different contest page for each course. So for each course there will be contest page. Like you can see, this was the page for graphs and trees. uh, the screenshot is outdated, but as of now there are, I think, 20 plus problems on this page. And apart from these 20 plus problems, I've also given 20-25 problems, apart from these, to the students, wherein which they can practice. And I had solved, I think, around 20-25 again on the on in the live classes itself, in the live classes only. So in totality, I don't know, maybe 70 to 80 problems have been discussed or given for practice, just for trees and graphs alone. And this is trees and graphs one. So this trees and graphs course is basically the first counterpart of graphs. So graphs two is still going to start. I am going to take it. So yeah, you can sort of get an idea the depth of uh, about the depth in which a particular topic is being covered, the number of problems that are being discussed or given for practice, right? So yeah, I think that's enough to give you an idea. So yeah, this was all about the course. So I'll just end with what the subscription plan is, how is it going to look like, and what you can do to sort of get it at a lower price as of now. All right. Uh, so yeah, these are the standard prices, right? For 1 month, if you want to buy 6 months, 6,000 per month, and 45,000 per month if you pay for 6 months, and if you pay for a whole year, then 2750 per month, right? So also I'd like to add, it's not like that you are going to pay for different courses. It is a subscription plan for the whole competitive programming module. So you buy the whole module, and then you get access to each and every course that is there on the platform, right? So I hope I've made clear what exactly is it. And uh, and uh, I know some of you may think that it is quite higher price. Here I'd just like to add one thing, guys. I think okay, let me explain it to you by my example only. When I started programming, I also spent around, I don't know, I think around 50,000 rupees on courses and stuff, learning different things. I took up a DSA course, and then I took up a computer programming course, and I also took up a machine learning course. And in totality, I think I must have spent around 50,000 rupees. And I still don't, I really, really don't regret it. I am grateful that I spent that money, because I was able to learn things in a much faster way as compared to I would have, uh, if, if I had done it by myself, right? So I think it'll really be worth the investment if you guys can afford. And there is an introductory deal in which you can get that 1 month subscription for rupees 1000 only. So I think it is a very good deal. You can, had I been in your place, I would have gone for this, and I would have bought it for 1 month, tried things out, and if I like it, then I would have sort of paid for the 6 months or the 12 months, whatever would have felt best for me, right? So you can use this you can use this referral code called Pulkit CP. If you use this referral code, PULKIT CP, then you will get this 1 month subscription for just rupees 1000. And also, I'll just add, this is for limited time, so please take your decision accordingly. Otherwise, you will get a 10% off on this 6 month subscription, and 10% off on this 12 month subscription. And after the limited time is expired, it will be available for 5400 rupees, right? So 10% off on the 1 month subscription as well. All right. So I think enough said about uh, the course. Let's just dive into the problem solving part now. I think just confirm if everything is fine. I'm visible, audible, no lag, right? Just please confirm it on the chat, and so that we can go ahead and start with the teaching part. Okay, people are saying that everything is smooth, so let's just continue. All right. So the agenda is breadth first search. All right. Cool. So uh, so when I'm teaching breakfast search, I'll sort of assume that you guys may have a little bit idea about graphs. If no idea at all, it is fine. You can watch the video, you can follow till the end, and you'll understand maybe 60%, 70% of things, but there will be some things you may be confused about. So anyway, if you don't know about graphs, you can also, after this class, go and check out other special classes that I've taken. I have covered basics of trees and graphs there as well. So yeah, so you can sort of, if you want to check out the other classes, this is the link, and basics of graphs have been covered there. Underscore Pulkit underscore C. All right. So yeah, let me just continue. So when we discuss about graphs, right? So one of the most basic things that may occur in our mind, that may come to our mind, is how do we represent graph, right? And maybe if you guys have an idea about graph, you know that generally we do it in the format of an adjacency list, right? So I'll just skip it for now because that's not the agenda of this class. And the next thing that comes to mind is traversing the graph in some manner, right? So there are two standard traversal techniques. One of them is called depth first search. You know depth first depth first search, Again, not the agenda of today's class. And another one is the one that we are going to discuss today, which is breadth first search. All right. So I can see this question that someone is saying, why has the previous video been made private? Okay, I'll check with the team why is it the case. I'm sure it will be some technical issue and uh, it will be undone. All right. So yeah. So let's discuss breadth first search. All right. So So the basic difference between breadth first search and depth first search, before starting with the basic difference, the the search the traversal algorithms basically mean that we'll start with a particular node, and we'll then keep then we'll traverse the whole graph in some manner, depending on what manner, that will depend on whether we are using DFS or BFS or some altogether different traversal technique on of our own. All right. So if we are talking about BFS, as the name suggests, we are going to go breadth-wise. All right. So let's take a small example and let me just discuss what do I mean by breadth-wise, right? So let's say we have this small graph with 5 nodes, 1, 2, 3, 4, 5. All right. Let's say there's an edge between 1 and 2 and 1 and 3 and 2 and 3. Cool. So let's say we start our breadth first search with 1. So what we'll be doing is, when if we start with 1, first of all we'll visit the node 1, right? And then we'll be visiting the neighbors of 1, right? The direct neighbors of 1, which is 2 and 3. And then in the next sort of iteration, or whatever you may like to call it, we'll be discussing the neighbors of 1. So then 4 and 5, which is neighbors of 1. So if you notice, if you know if it was a sort of, for example, if it was a tree, right? If it was a tree, so if you notice, then first we are visiting the first level, and then we are visiting the second level, then the third level. So we are basically moving breadth wise, right? Breadth wise. All right. uh yeah. So I'm just reading a comment. We'll cover breadth or width, then we'll forward. Yeah, right. What you are saying is correct, even. Okay. So yeah, this is what it is going to look like. And now let's just sort of dive a little more into how exactly can we implement it, right? So we'll be having sort of a data structure, right? Wherein we'll be storing some nodes, and we'll visit them in some order, right? So like I said, the first thing that I want to visit is going to be 1. So let's say in our data structure as of now, we have 1. Then what we can do is, since we know that after 1, the next nodes that I'm going to visit, that I'm going to cover, are 2 and 3, which are the neighbors of 1. I can just add the neighbors, right? And so I've visited 1 now. So after having visited 1, I know that the next sort of uh, nodes that I'm going to visit are going to be 2 and 3. So I visited 1 now. I've deleted it from the data structure because I do not have to visit it anymore. But I know that the next nodes that I have to visit are going to be 2 and 3. So I've added those to the data structure that I'm going to use to implement the BFS, right? So now I have 2, right? So I'll just delete 2 from my data structure because I have visited 2. So I have visited 1. Uh, just let me uh, change the color. So I visited 1, and then I went to 2, and so 1 has been done, 2 has been done, right? And I don't know what happened. The color of everything changed to red. All right, now it is fine. So yeah, so then we have visited 2, and as soon as we visited 2, then also we know that at a particular point, when I am 2, right, and I know that 2 is a direct neighbor of 1. If I'm at that if I'm at a direct neighbor of 1, I know that all the other direct neighbors have already been added to the data structure, because we know, we can see that 3 has already been added to the data structure. But now I know that after having visited, the neighbors of 1, I also have to visit the neighbors of 1, right? So I'll just go to the unvisited neighbors of 2, and add those as well to the queue. But when I go to the neighbors of 2, if you notice that 1 I've already added to the data structure, 2 I've already added to the data structure, 3 I've already added to the data structure. So now when I'm going to traverse the neighbors of the 2, I am going to find 1 and I'm going to find 2. But I'm going to find 1 and I'm going to find 3. But both of them all have already been added to the data structure, so do nothing, right? And then I'll then the turn of 3 comes. We'll just delete 3 from the data structure, and then again I'll just visit the neighbors of 3. And when I'm visiting the neighbors of 3, I'll just see that there's 1, but 1 has already been added to the data structure. And I'll be visiting 2 again. I added 4, and 5 will not have been added, so I just mark them as added, and also add them to the uh, yeah. And now I have also printed, or whatever you may call it, visited 3 again. Then coming to 4, 4 has been deleted, but now 4 has no unvisited neighbor. All right, then 5 has been visited. Now the 5 turns comes, but again 5 has no unvisited neighbor, so done. So uh, now we have sort of popped out each number from the data structure, and there is nothing more left to be discussed. Okay, Sai, I'm not sure why you are asking this question. uh, I cannot sort of explain the problem in just 30 seconds. I'm just answering the comment. But I know that I had the same session on the Unacademy platform, and I discussed a problem there. So the problem that I'll be discussing today will not be same as that problem. The problem that I'll be discussing today will be different one. So if the reason behind the question was that, so maybe you should stick around, because I'll be discussing a different problem. All right. Okay. So I hope I answered your question. So coming back to the BFS itself. So if you notice, right, we have and yeah, then again, then we would have visited 4, and we would have visited 5. All right. So now what I want you guys to notice here is that what we are doing is, in the data structure, we are always deleting the nodes that were inserted earliest, right? Because first we popped out 1, then we popped out 2 and 3, and then 4, and then 5, right? And we are adding the nodes in the end, when we are adding the nodes from the right. If you notice, we are popping the nodes in the order of, the earliest being pushed will be popped earliest. So what we do is we call it first in, first out. So yeah, Pankaj has written exactly what I was anticipating. Anybody of you guys, any one of you guys to write. So the optimal data structure in this case will be Q. All right. So yeah. Uh, so this is what a BFS is going to look like. I'm sure that you guys may have an idea about a vague idea about how we are going to implement it. Maybe not exactly, but a vague idea. I hope you get it, that we'll be using a queue in some fashion. And then when we are popping out the front node of the queue, then we'll visit, then we'll iterate on its neighbors using adjacency list, and then we'll see what all neighbors have already not been added to the queue. We'll add those to the queue, right? You guys are getting an idea, right? Plus, just please write on the comments if you are getting me as of now, or is it that everything is going over your head? Okay, I'm waiting for some comments to come in. Just a second. Okay, so just one person has written. All right, if you guys don't want to be interactive, that then I'll move on. But I suggest you to be interactive. That way you'll also enjoy and I will also enjoy. Otherwise, you may get bored. Uh, okay. So I'm getting some uh, doubt. Okay. Shringu, implementation is something that we'll cover right now. All right. So I'll just continue. Just try to be involved, right? That way we'll both enjoy. We will, you and I, everyone will enjoy. Yeah. Okay. So yeah, the other thing that that may be noticed here is that when we are pushing the nodes in the queue, right? First we pushed the node 1 to the queue, right? Then we know push the nodes 2 and 3 and then 4 and 5 and so on and so forth. So first the node itself, then its neighbors, then the neighbors of its neighbors, and so on and so forth, right? So what I'm trying to tell you guys here is the nearest neighbor, the nearest nodes will be pushed first, and then the nodes having a largest distance will be pushed. So what I'm trying to say here is, if a node A, uh, just hear me out, if a node A is pushed, a node A is pushed before a node V, yeah, let's just use do and V instead of into the queue. Distance of the node U will be less than or equal to distance of the node V. This is another observation that I want you guys to draw here, right? Just because of the reason we are doing breadth-first search, so first neighbors, then neighbors of neighbors, and so on and so forth. All right. Another thing that I want you guys to notice here is that if we uh, if we sort of draw a tree, right? If we notice, then 2 was being pushed through 1, right? When we were exploring the neighbors of 1, we pushed 2 and 3, right? And then when we were exploring the neighbors of 3, we pushed 4 and 5, right? So if you notice, we can also sort of draw a tree out of this BFS algorithm, wherein each node's parent will be that node through which I am being pushed to the queue. So if I draw the BFS tree for this particular case, it is going to be 1, 2 and 2, 2 and 3, and then 4 and 5. Because 2 was pushed using 1, right? Because when we were iterating through the neighbors of 1, we pushed 2 and 3, right? So the parent of 2 and 3 is 1, right? And then when we were iterating through through the neighbors of 3, we pushed 4 and 5, right? So so let's say the the parent of 4 and 5 is 3. So we can also get a tree like structure, uh, if we want to, just for having an idea about how did things go during the BFS. Now I'll just tell you what its significance is, right? Uh, how can it be useful, right? So yeah. Now the next thing that I'm going to say is, then we'll come to how BFS tree is going to be useful. Is then that when we are sort of pushing nodes to BFS, it will be sort of through the shortest path. For example, let me use the highlighter. So for example, if we see this path, uh, 1 2 3, we have this one path. 1 2 3, we have this another path, which is 2, which is of length 2. But since this one is the shorter path than the 2, this 3 will be pushed, this 3 will be considered as a direct neighbor of 1 and not the neighbor of neighbor, because in the best case we can reach 3 through just one edge, right? So what I am trying to convey here is that BFS will also help us in getting the shortest distance to each node from the source node. So I'll just also explain this to you by using an analogy, I think, which I think is beautiful. So BFS can help in getting single source shortest paths for undirected, uh, for unweighted graphs, sorry, not undirected, for unweighted graphs, right? Because there are, if there are some edge weights associated with the nodes, then things are going to change. I hope that it is clear. Unweighted graphs. All right. So let's come to the analogy that I was uh, talking to you about, that I was telling you about. So imagine for this graph, right? Let's talk about this graph. Imagine that each node is a bead, and if there is an edge between a node A and a node B, let's say there is a string. Let's say that those two nodes are being attached by a string of length of equal lengths, okay? Or let's say the length of each string is, I don't know, maybe 5 centimeter or something, right? So when you are applying BFS from the source, for example, if we are applying BFS from this node 1 in this case, imagine that you hold the whole system with by holding the node 1, okay? So gravity will do its work, and then let's see how will the sort of system look like. So what will happen is, this node 1 will be at the top, but like we would have holded it, whatever, drawing is not really something that I'm good at. All right, we would have holded it, right? So uh, then the nodes 2 and 3 will be there, connected by these edges, these strings that are there between 1 and 2 and 2 and 3. And then we would have this 4 and 5, right? 4 and 5, right? And there will be this another string which would have loosened itself. So 2 and 3, the string connected 2 and 3 would have loosened, and the other strings would be tight, right? So I hope you get an idea that when I'm applying BFS, I'm doing something which is very similar to this. Some strings will be tightened, some strings will be loosened. So through this tree, I'm just trying to sort of uh, show you guys some of the strings, some of the edges which are not loosened, which are tightened. All right. So here we can see that the distance of 3 and 2 is going to be 1 from the node 1, and the distance of these nodes is going to be equal to 2. All right. So if we are to calculate the shortest distances, now here's when the DFS tree comes into picture. What I can say is that the distance of a particular node U, and when I say D, I mean distance from source. All right. So keep this in point. D means distance from source. Cool. So so what I'm saying is the distance for a particular node U is equal to the distance of parent of U plus 1. So if 3's distance is 1, then 4's and 5's distance will be 2. So this is what I'm trying to sort of explain to you guys using this analogy and the DFS tree. And this is where the DFS, the BFS tree, sorry, breadth first search tree will come into picture. We can calculate the distances, and also we can get the actual path also. If you notice, if I try and climb up the tree using these edges, if I let's say I want to get the path of 5, the shortest path of 5 from 1. So if I keep climbing up, let's say the node is 5, the last node is 5, what will be the second last node in the path? The parent of 5, which is 3. What will be the third last node? The parent of 1, the parent of 3, which is 1, and so on and so forth. So this BFS tree can also be used to calculate, to get the shortest path from source node to particular node. So it may not be exactly clear how we can do so. This is something that I'll be covering in the coding part. We'll just spend, you know, maybe 5-7 minutes more for this, and then we'll jump onto the question. But please give me please tell me if the idea is clear, if everything is clear, and let me know if there is something that you guys want me to repeat. I'm waiting for you guys to reply and comment on the chat. Not exactly comment on the chat, text on the chat. So also guys, there is a, I think 10-15 seconds delay from between when I speak and when you guys actually listen it on listen it. And so I'll just receive your messages 10-15 seconds later. Okay, please explain last line. I'm just saying that the distance for a particular node can be said that it is equal to the distance of its parent plus 1. So I am just trying to explain here that uh, just a second. So for this node, we know that the distance of 1 from 1 is 0. And we also know that 1 is the parent of 2 and 3. So you can see that 1 is the parent of 2 and 3. So distances of 2 and 3 are equal to the distances are equal to the distance of their parent plus 1. The distance of their parent is 0 and their distance is equal to 1. So this holds true. And again, you can see for 4 and 5, the 4 and 5, the parent of 4 and 5 is 3. And in the case when we apply BFS from 3, BFS from 1, sorry. And in this case as well, you can see that the distances of 4 and 5 are 2, which is equal to the distance of their parent plus 1. So so since when I am coming through the shortest path from one to a particular node, parent of that particular node basically represents. Okay, so you're saying that you have got it. That's great. Okay, all right. So I think I've gotten some of the messages on chat, and people are saying that they've understood. So maybe I'll just start with the implementation part now. So yeah. Uh, so like I said, when we are, let me just share my screen. I think the screen is visible. Yeah. So we'll have initially taking the input, which is the number of nodes and the number of edges, and we can have the adjacency list in this format, vector of vector in DDJ. And don't be scared by this whole thing. It is just a template. I've just predefined some things to their short form sort of, so that I don't have to write it every time. For example, when we use vector, we have to generally write pushback. So I've just defined PB as pushback, so I just have to write PB. Don't be scared. I just keep telling you whenever I'm using something. Uh, okay, I've scrolled to the top of the screen. Jagannath. All right. So I'm just coming back now. So this vector of vi will do the work of the adjacency list. All right. So vector of vector int is there, and I'll have to resize it to n plus 1 because there are n nodes. All right. Now I have a vector of size n plus 1, right? So you can visualize it like an array of array of size n plus 1, where each element is a vector. All right. So then I'll just take the edges. So while m minus minus means I'll just run this loop n times. So scene uv, And since I am talking about an underacted graph for now, so u dot pushback v and v dot pushback u. All right. So by this point, I have my graph ready. The number of edges are n, the number of the number of nodes are n, the number of edges are m, and I've added the values to wherever I had to add it on the adjacency list. All right. So now I'll just, let's say, call the BFS function from the node 1. All right. For now, I'll just print these nodes in some manner. So void BFS int src. Okay, I am getting this question. Is there any advantage of using in32T? Evan, I'm sorry if I'm pronouncing your wrong name. If I'm pronouncing your name wrong. So in32 is equivalent to the normal int that we use. So the thing is that in some problem it happens that integer generally gives us overflow because the answer can be up to 10 raised to power 18 or something like that. So what I have done is I have defined this int as long in the line 8. So if I write int here, it'll sort of visualize it as long, and long means something that we cannot use. So this is why I have written int 32. All right. So yeah, I'll just go ahead and discuss the BFS function now. So we have our source, right? And now, like we discussed, we'll need a queue to have queue int queue to have sort of an idea about what all things are there in the queue right now, and so on and so forth, right? And then we'll also need a uh, boolean array, let's say done or added, of size n plus 1, which will initially be initialized to 0, which will basically tell me that has this particular node been added to the queue or not, right? Like we discussed, we just have to add the unvisited neighbors of the current node to the queue. So I'll need to have something which can tell me that whether it has been added or not. Cool. So yeah, so initially what I'll do is I just add the source node to the queue, right? So source node has been added to the queue, and then while the queue is not empty, all right. So while the queue is not empty, what we will do is we will just get the current node from the node from the queue, the front node from the queue. I'll just pop it out. I'll just print it, right? And then we have to visit the neighbors of this node. So for int neighbor belonging to adg of current, so we'll visit the neighbors of the current node, which can be iterated like this. So if a particular neighbor has not been added, if the neighbor has not been added, what I'll just do is q dot push that particular neighbor. Sounds good or not? There are some mistakes in the code. uh, i'm 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 waiting for you guys to point them out. They're in the BFS function only. Tell me, where are these mistakes? Okay, added should be updated. That's nice. So added of NB should be equal to 1. Again, bilkul, right. Jagannath, you are right. That's what I was expecting. There is one more mistake. There is still one mistake in the code. So yeah, like I said, if the current neighbor has not been added, we should add it to the queue, but also we should update the added value, right? Because otherwise, when we'll next time try to add it, when every time we'll see that it has not been added. So there is still one mistake. Let's see if you guys can figure it out. Yeah, right, exactly. So So when we are adding the neighboring nodes, when like when I said that edit should be updated every time, right? So then we'll need to make sure that we are updating this edit array. Or I just update it to Viz. It sounds more intuitive, right? So I'll have to update this Viz array every time I'm pushing a node to the queue. So I updated it here, but but did not update it here. So when we are adding this source node to the queue, then also we have to update this visited array for the source. So yeah, now I think uh, okay. So there are some mistakes. So one is this n value. N value should be declared over here, right? Yeah. Let's see if there are any other errors. Okay. I think I by mistake just used the one angle bracket. There should have been two angle brackets. All right. So I'll just try and run the code for the case that we saw. So there were 5 nodes in that case, and I don't know the number of edges. 1, 2 was there, 1, 3 was there, 2, 3 was there, 3, 4 was there, and 3, 5 was there. Right. So there are 5 edges. So let's just try and run it. So yeah, 1, 2, 3, 4 is exactly what we were expecting. So uh, this was the graph 1, 2, 3, 4, 5. All right. So started with 1, added 2 and 3, and then 2 will be popped out. So 2, and then 3 will be popped out. Then 3, and when 3 will be popped out, we'll insert 4 and 5. So 4 and 5. So while we are coding and printing the BFS, I want you guys to realize that there can be different possible BFS sequences. It is not that this is the only possible BFS sequence if we started from one. So it just depends that in what order are the nodes added. For example, had it been the case that 3, 5 is written before 3, 4, then this 5 and 4 would have interchanged. So if I run it again now, you'll see that this 5 and 4 will be interchanged, like you can see. So because now 3, 5 wala edge comes before the 3, 4 wala edge, uh, 3 and the node 5 will be inserted to the queue before 4 has been inserted. So in this case, I hope this is clear that it is not always the case that this BFS sequence will only be printed. All right. So yeah. So enough with the uh, BFS. Now what I want is I want to implement another BFS function. Let's say BFS1, and I want the distances of each node from the source node. All right. So for that, I'll need to have another array which is vector int d n+1 size, and let's say initialize it by -1 for now. All right. So when I'm pushing the source node, I know that the distance of the source node from source is going to be 0 only, right? And and like we said that for any node, the distance of that node is going to be the distance of parent plus 1, right? So now when I'm pushing these neighbors, I need you guys to understand that the current node is parent of the neighbor node, because the neighbor node has been visited through this current node. So this neighbor node you know uh, comes in the subtree sort of is a child of this current node, because the neighboring node has been added to the queue through this current node. So since the current node is the parent of the neighbor node, so when I am pushing the neighboring node to the queue, what I'll just do is the distance of neighboring node should be set as the distance of the current node plus 1. Cool. So and then I just return this distance. I think everything is cool right now. Everything is cool till now. Uh, so so yeah. Once we are done with this, we can just print all the distances and check if it makes sense. So I just print every node I and the distance of that node I from. Okay, so I just erase this C out so that it is easy to see the distances. Yeah. So distance of 1 is 0, 2 and 3 is 1, 4 and 5 is 2, which makes sense, right? So also let's say we had another node. Let's say the number of nodes were actually 6 instead of 5. So now let me again run it. Yeah, so now you see that the distance of 6 is -1. So what I'm trying to say here is I initialize the distance array with -1. So it is possible that a node is not reachable from one, right? Since you know that there is no edge from the node 6. So the node 6 is a different connected components of its own, and we cannot visit 6 from 1. So the distance will remain -1 for all those nodes which cannot be visited from the current node. -1 or whatever default value you initialized, whatever default value you used to initialize your distance, right? So yeah, I guess this is it. And the other thing that I wanted to cover for for BFS was printing the distances, right? Sorry, printing the paths, right? So like I said, for printing the path, what we can do is we can just climb up the parents till we reach the source node, or till we reach the, yeah, till we reach the source node, and we'll have the path in reverse order, right? I just also showcase it right now. So yeah, so what we can do is we can also have a parent array. Let's say, let me make another, uh, let's say this BFS1 is actually BFS distance, which gives me the distance array. Let's say we have this another BFS which gives me the parent array. So, so let's say I have this parent array with again n plus 1 size and initialized to, let's say, -1. All right, and let's say the parent of the source node is -1 only. It's up to us whatever you want to give the value. So I'm just giving parent of the source node as -1 because -1 is the node number that is not going to be equal to any other node, because the numbering of the nodes is 1 to n, right? So I can give the value 0 or -1 to sort of indicate that this particular node is a source node, right? So when I'm iterating through the neighbors of the current node, then earlier I was updating the distance, but now I just want the parent. So I'll just say parent of nb equal to current, right? So yeah, so at the end we'll have the parent array and we can just return the parent array. Yeah, so it is compiling. So let's say we have the parent array as well, BFS of parent. All right. So yeah, so what we can do is we can print the paths. So let's say I just, for every node, right? For every node, what I want to do is, let's say, print path I, and with the path with the node I'll just pass the distance and parent array, right? So I need the distance array and parent array as well for printing the path. Why I need the distance array and not just the parent array? Because the distance array will tell me that uh, that is it possible to visit the current node or not. So using distance array, I'll just come to know that whether is it possible to visit the current node from the source node or not. All right. So I have this print path function. Let's say print path int current node and vector int distance and vector int parent. I've just passed these through reference so that I can save some time, because otherwise printing each sort of uh, node, I'll have to just pass this GMP array every time, and copying it will take a lot of time. So I just passed it through reference. All right. So now if uh, the distance of the current node equals -1, it means that it is not possible to visit the current node through the source node, whatever source node we are talking about in the code. Currently, we're talking about one, right? So I'll just print I and I'll just say no path. All right. Otherwise, I know that there is a path. Let's say I'll just initialize a vector int path. And now what I can do is while current value is not equal to -1, because I know that the parent of the source node will be equal to -1, right? So while I am not reaching that node -1, I'll just climb up the BFS tree and keep pushing the values there. So path dot pushback current equals to parent of current. So I just push the current value and assign the parent of current value to the current value. So I'll just explain it to you in a minute using an example. All right. So so once I have the path, I'll have the path in reverse order. So I'll just reverse it. Now I have the original path. What I'll just do is print the current node. Okay, it should not be I here. It should be current. Print the current node, not exactly current. Okay, so there is a mistake. The current node would have already be equal to -1, so it will gives us a mistake. So I'll need to have the original node's value saved here. So I'll just print I here. Okay, I hope you understand. Had I just printed current here, it would have given me it would have given me wrong value, because I have already updated the value of current to -1, right? So I'll have to print I here, and then I'll just print the uh, and I don't know, node to belonging to path cout node, and then an enter key. All right. So okay, this PAR is wrong. It should be P, because I've just used the word P here. Right. So let's just try and print. Let's just try and call it. Okay. So you can have a look here that the path of one is just one itself. Path of two is 1 2, and three is 1 3, and 4 and 5 is 1 3 4 and 1 3 5, and for six there is no path. So I'll just draw it once. So the graph was 1 2 3 4 and 5 and 6. So yeah, this is what the shortest paths would have been like, and it is what it is. It is what they are like, right? So so yeah, please let me know if it is clear or not. If it is, now we'll move on to the problem solving part. Will Oh, okay, the annotation is not visible. Okay, so so now it will be visible. I'll just draw it again. Whatever, just I had just drawn the graph. So this was the graph. So I was just saying that the paths that have been printed are equivalent to what should have been printed, right? So yeah, that's what I was saying. So yeah, please let me know if all the things till now are clear. And now we'll move on to the problem part. The problem that I'm going to discuss is a really good problem. It will take 20 more minutes to discuss the problem, 20 to 25 minutes maybe. So for those who guys can stay, you're welcome to stay. I'm waiting for a response. That is it clear? Is if there is any doubt, then also give a response maybe. All right, that's great. So I'll just share the problem. What the problem is now. Uh, all those guys who are still there and want to stay till the end, this is the time that I request you to pay the most attention, because since I'm explaining the problem now, if the problem will not be clear, you'll just be lost during the rest of the class, right? So please try and pay attention to the part when I'm explaining the problem. All right, just give me a second. I'll just Yeah, so the problem goes like follows. uh, Given an undirected graph, okay, and nodes, images. Uh, each edge has each edge is either red or green. All right. So each edge has a color associated with it. All right. So this is something which I've added. So every edge is either each edge is either red or green, and you are being given a source node, uh, a source and a destination. All right. So these are the things that we are being given. An undirected graph with n nodes and m edges. Each edge has a color associated with it, which is either red or green. And we have been given a source node and a destination node. So what we have to do is find the length of shortest path from SRC to uh, to destination. And if the question was just this, find the shortest path from SRC to destination, and also it is being given that the weights are one for each edge, so the graph is unweighted. If this was just the question, it would have been pretty simple. We have already covered it. Just apply BFS from the source node, and whatever is the distance of the destination node, which is our answer, right? So but the question is find the length of the shortest path from SRC to destination such that following conditions are met. Such that basically you start with the red edge. So what do we mean by this? Just a second. So basically, when we start from the source node, the first edge, the first edge that we traverse should be a red edge. All right. So this adds some constraints, right? So the first edge should be the red edge. Second is that you end with a green edge. All right. So the last edge that you traverse, just before reaching a destination, should be a green edge. And third is you can switch from a red edge to a green edge just once. So you start with a red edge, you end at a green edge, and in between, you can switch from a red to green just once. So I'll just give you an example, and I'll ask you guys only whether or not is this a valid path or not. So 1, 2, 2, 2, 3, 2, 4, 2, 5, let's say. All right. So 6. So we have this, and we have this, and we have this, we have this. Let's say we have this. Let's say we have this. Right. So Mm, just give me a second. So also let's say we have this, and then we have another node, let's say 7, and it is like this. All right. So now let's say we have this graph, and we have to reach from, let's say the source node is the source node is 5. The source node is 1. Sorry, the source node is 1, and the destination node is 5. All right. So so this path 1 to 3 to 4 to 5, it is not a valid path. Why? Because okay, we are ending with a green edge, it is fine, so condition 2 is satisfied. But how many times are we switching from a red edge to a green edge? Okay, once, it is also fine, right? uh, but the first condition is not fine. We are starting with a green edge, so this is not a valid path. All right. And regarding this is a valid path. This is an example of a valid path. All right. So we are starting with a red edge, we are ending with a green edge, and we are switching from a red edge to a green edge only once. So this 1 2 4 5 is a valid path. All right. Uh, and this 1 2 6 7 5 is again not a valid path. Why? Because we are starting with a red edge, but we are ending with a red edge. But sorry, we are ending with a green edge, which is fine. But we are switching from a red edge to a green edge twice. All right. So it is also not a valid path. So out of all those paths which are valid, we have to find the uh, we have to find the shortest path, right? So in this case, I think only one path is valid. Mm, rest, there is no path which is valid. So this so the answer is going to be 3 in this case, right? But let's say there was uh, one one more node, let's say 8, and it was like this, and it was like this. So in this case, the answer would have been 2, right? Because there are two valid paths. The path number 1 is 1 2 2 to 3, sorry, not 3, 1 to 2 to 4 to 5, and another valid path is 1 to 8 to 5. All right. So in this case the cost is 3, and in this case the cost is 2. So 2 is our answer. All right. So I hope the question is clear. I'll just quickly repeat the question in 2 minutes, and in the meanwhile, you guys can tell me if the question is clear. If something is not clear, we'll discuss the solution. If you guys have anything for the solution, and please write the solution only if you haven't heard of the question before. Otherwise, you'll just spoil it for the rest of the people. Uh, I'll just repeat the question now. All right. So we have been given an undirected, unweighted graph with n nodes and m edges, but the catch is that each edge has a color associated with it. The edge can either be red or green. All right. And we have also been given a source node and a destination node. So what we have to do is we have to find the length of the shortest path from the source node and to the destination node, such that we have to follow these conditions. So we have to start with a red edge only. We cannot start with a green edge. We have to end with a green edge only. We cannot end with a red edge. We can switch from red edge to a green edge only once, right? So I just gave you an example here, and I think I've spent enough time, trying to explain uh, what all are valid paths, what all are not. So in the end, we boiled down to these two valid paths. So these two were the valid paths, right? So out of these valid paths, the distance of the distance when if we traverse to the first path was 3, and for the second path was 2. So our answer is 2. So in this case, the answer is going to be equal to 2. All right. You can assume that if there is no valid path available from, you know, one to, from source to destination, you can maybe print -1 or something. So again, I'm asking you guys again, yeah, please write it down in the chat if it is clear, or if it is, or if it is not. If it is clear, if you have approach, if you have an approach in mind, then also you can write it. Okay, Anu is saying that it is a nice question and it is clear. uh, okay, all right, that's great. So spend some time, think think about the solution. uh, how can it be solved? I'll just give you hint as well, before we actually get to the solution part. Like I have said, that we can, switch from red edge to green edge just once. So I just need you to imagine. I'm not going to draw it down. Just imagine it, because maybe draw करने से शायद थोड़ा hint मिल जाए. Anyway, so but the thing is कि initially there will be a bunch of red edges. So first edge that will traverse will be red. Second will be maybe red or green, and so on and so forth. So what I'm trying to say is it will be red, 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 and then after a particular point, green, 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 and so on and so forth. So it's just red once. It's the first few edges are going to be red, and then just switch once, and then the last few edges are going to be green. So once we switch from red to green, we cannot come back to red, because if we come back to red, then we'll have to go back to green, which will result in switching from red to green twice. So I hope you get an idea. It will be just a bunch of red edges, and then just switching once to green, and then a bunch of green edges. So maybe try to think somewhat now, because initially we are just using the red edges, and then we are just using the green edges. Yes, even one vertex can have more than one edge. I think it has been made very clear with this example. I'm not sure if I'm understanding your question properly or not. You can see that this two has three edges, one this, another this, and another this. Am I not understanding the question? Yeah, more than two also. And for two, for the node two, more than two edges are associated with it. So any thoughts on the solution? Anyone? So I'll just draw it down what I just said. Uh, so when we are starting, so there will be the source node. There will be a bunch of red edges, and through some path will reach a certain node X, maybe, we don't know. So, and then there will be a bunch of, I don't know, maybe even one, but a bunch of green edges, and then we'll reach the destination. Someone is saying first we will traverse through red and then green. If we get destination, then it's answer. Okay, I don't know. Like maybe you are thinking in the correct direction, but from just this one sentence, I cannot really understand what you are trying to convey in a very complete manner. So I just continue. All right. I think it's best that I continue, because even I understand that explaining all of your thoughts in just using this chat is not very feasible. So what I'm getting to here is, okay, if you are saying Floyd Warshals, and I'm not really sure that how will you use Floyd Warshal for making sure that you first use red, and then in the end you use the green, and you just change from red to green just once. I'm not sure. Generate all possible paths and narrow. Yeah, if you generate all possible paths, yeah, maybe you'll be able to solve. Yeah, definitely you'll be able to solve the problem, but you'll end up taking a lot of time in this problem. Let's say we are being given that the number of nodes and number of edges are greater than equal to 1 and are less than equal to 100,000. So 10 is to power 5. So it will not work in those constraints. All right. So let me just continue then. All right. So let's say let's say now pay attention. Okay. So we are starting from the source node. Let's say we visit a node x. This x node is the arbitrary node. I don't know what this x is going to be. So it is just a variable. Okay. So let's say after x, then I start traversing through only green edges, right? So what I am trying to tell you guys here is, for this particular general case, let's try to calculate what will be the distance. Distance will be equal to distance from source to x using just red edges, right? Plus distance from x to destination using just green edges, right? I hope it makes sense. So if I just want to calculate the shortest distance, if I switch just after node x, so there has to be a point when I switch from red edges to green edges, right? So let's say if I just switch from red edges to green edges after just after a particular random node x, so in that case the shortest distance is going to be equal to the shortest distance from source to x using just red edges, right? I just try to visit this node x from source using just using just red edges, and I just find the shortest distance. How we'll do it, we'll just get to it in a short while, but let's just try to understand the essence of it. And then I know that from this node x, I have to visit this, I have to reach this node destination, right? So plus shortest distance from this node x to destination using just green edges. Please sort of give me an idea if what I am trying to explain right now makes sense to you guys, uh, or does it not, or is it difficult to digest? Do you want me to repeat? Please give me something so that I can make sure that it is a good experience for you, then and you actually get to learn something new. Okay, so I'm seeing a couple of messages that you guys have understood. Waiting for a negative one so that I can maybe repeat if there's someone who hasn't understood this. All right, if I do encounter encounter a, a text, then I'll just repeat. Otherwise, I'm just going to uh, you know continue. All right. So calculating these is not that tough. Can be done using BFS. So uh, just tell me this thing. If I iterate over each node, right? Let's say I have this value for each node, right? Let's say I have this using just red edges. Okay. Uh, let's say I call it DSR. DSR basically means distance from source using red. Okay. Just I'm just writing it in short. a little lazy. So distance from source using red, and let's say we call it DDG, distance from destination using green. All right. So can I say if I iterate over every node, let's say for uh, I equal to 1 to n, in general, okay, there are some more cases that have to be handled. For example, if I equal to source or I equal to destination, then we have to continue. But in general, I'm just saying in general, okay, answer equal to min of answer comma dsr or I of I plus ddg of I. Right, I hope it makes sense. So what I'm just doing is I just told you that if I am to uh, if I am to switch from red to green exactly once, right, because we know that we'll have to do it once, so red to green exactly once. So I am trying for each node x, for each node, that if I make this transition just after visiting the node x, right? So then what will be my answer in best case scenario? So I'm just trying this for every possible node, and in that case I'm just taking out the minimum, right? Also before this we also have to make sure that that it is all, that it is actually possible to visit the current node from the source node using only red edges. And just let me tell you what I mean. So what I'm trying to say here is I also need that if dsr of I equal to -1 or ddg of I equal to -1, then just continue, right? If it is not possible to reach, then also I have to continue. I'm sorry for this bad handwriting. Then also I'll have to continue. All right. So otherwise, I have to do what I just told you guys. So, yeah. All right. So, so just once again, please confirm. Does it make sense to you guys? What I've just told and written. So the thing that is left now is to how to calculate this DSR and DDG. Yes, Vivek, that was a long time ago. But let's not divert from the topic. Please tell me if it is clear or not. The only thing that's left now is to calculate this DSR and DDG, which is very simple. All we have to do to calculate these DSR and DDG values is we just run one BFS, sorry, we'll just run one BFS. Okay, the min block again. Okay, so let's say we have initialized our answer with a very large value. I don't know, maybe infinity or something, 10 raised to power 18 or 10 raised to power 9 or something like that. And we'll just iterate for every node. We'll go to every node from 1 to n, and we'll just check that if we transition from if we transit from red edges to green edges through this node, right? Like I said, that in general, if we if shortest distance, if I switch just after node x, will be this distance, right? Will be equal to this. But I don't know that what is the optimal value of x, right? So for what can be the possible values of x? 1 to n. So for every value from 1 to n, I just check that what will be the value of my shortest distance if I just switch from red to green just after this node. And I'm just trying to calculate the distance for this particular node, and I know that the distance is equal to dsr of I uh, plus ddg of I, right? So So I'll just take minimum out of all those values, and the minimum value will be my answer. But before that, I'll just have to check these two things, that if DSR of I is equal to -1 or DDG of I is equal to -1, then I'll have to continue, because if either of these values is equal to -1, it means that it is not possible to visit this current node using just red edges from source, or is it not possible to visit the destination from the current node using only green. All right, then I'll have to continue. And also, if the current node is equal to source or destination, then also I'll have to continue. uh, yes, Ame, you are right. Then also continue, but why this, why cannot the x and x will, why cannot the x be equal to source or destination? Simply because if I just switch after the source only, then my path will look like this, green 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 green, then the path will just be green only. And if the x value is equal to destination, then my path will just be red edges only. So this is why the x value cannot be source or destination. It has to be some other value. All right. So yeah, I hope the thing is clear. Let me just read. Someone is saying that BFS from source to find DSR, BFS from destination to find DDG, then just loop. Exactly, that's what we have to do. But all we have to take care is that while we are running the BFS from the source node, we have to consider only red edges in that BFS. And when we are running the BFS on the from the destination node, we have to consider only green edges. This That's something additional that we have to just take care of using while running BFS. So Anu is saying, so for as from so we do BFS from source to every node only red. Okay. uh, and then from sum of destination common nodes for both steps. Yes, Anu, your answer is absolutely correct. All right. So I'll now just simply go to Sublime, right? Let me just open another file, and I'll just quickly now code it out. Try to be alert and follow me. Uh, the standard thing, n comma m, the number of nodes and number of edges. And let's say again that we have the vector of vector int adj. All right. So let's say let's make this n global. And yeah, adj dot resize n plus 1 while m minus minus. Also, yeah, I'm sorry, in this case this vector of vector int will not work. We will need vector of pair of int comma bool, because we also need to store for each edge that whether or not is this edge red, like is this edge red, or is this edge red or green. We need to store it. So let's say 0 represents red, and 1 represents green. All right. So taking the inputs is like int uv color, in uv color. So adj of u dot pushback u comma color, adj of v dot pushback u comma color. Right. Let's say our input is also coming in this way, that 0 represents red and green, 1 represents green. Right. So I just say cout get min distance. Uh, Also, we'll be getting a source node and a destination node, right? So let's say we have this int src comma destination, which are all right. Cool. So yeah, vector of pair intent. I think yeah, it's fine. So now just implement this get min distance, uh, int src and int destination. All right. So what I'll do is, let's say I'll just modify my BFS function, so that the BFS function takes a color with it, and it just considers those edges which have that particular color. So let me just copy the BFS distance function from the earlier code, right? So, so let's say it takes a node source and it also takes a color. All right. So now I have this queue, I have this visited array, and so on and so forth. Everything is fine, but it's just that initially, if you notice, I was just I had these things, right? So when trying to push the nodes, the neighboring nodes to the queue, what I'll do is before pushing the nodes, what I'll just do that if the current node has already been visited, or the color of this particular edge, right? So also this neighbor is not going to be equal to uh, it is going to be equal to pair of int comma bool now. So ed, right? So let's say int nb is equal to ed dot first, and int color is going to be equal to ed dot second. So if the node has already been visited, or the color is not equal to let's call it current color. Okay, if the current color is not equal to the given color, then I'll continue, right? So now the BFS distress function is getting this source node and this color, and all those edges having a color unequal to the given color, I'll just not consider that. All right. So now in this min distance function, let me just initialize my answer with this infinity value, or I don't know. Let's initialize it using n by n plus one, because the maximum distance that can be possible is going to be n minus one only. Uh, yeah, I think the maximum possible distance will be yes n minus one. Yes. So let me just initialize a bit by n plus one. So what I'll just do is int dsr equals to bfs distance from source using the color 0 only, and then ddg equals to bfs distance of destination using the color 1 only. So I have these dsr and ddg values. So I just iterate again. If I equals to source, or I equals destination, or uh, dsr of dsr of I equals minus 1, or ddg of I equals minus 1, I just continue. Otherwise, I'll just do answer equals to min of answer comma dsr of I plus ddg of. All right. In the end, if answer is equal to n plus 1, it means that I had no valid path. I'll just do answer equal to minus 1 then. Otherwise, also I can do it like this as well. Return answer equals n plus 1. If yes, return minus 1. Otherwise, return answer. So this is a ternary operator. So it will return minus 1 if answer is equal to n plus 1. Otherwise, it will return answer. All right. Let me just try and compile. So okay, so it should not be int. It should be vector int. Okay, so rest of the things are correct. So please let me know if if things are clear. So I'll just in the meanwhile I'll just walk you guys through the code very quickly again. So took the input for n and m, resized the adjacency list to n plus 1, and then the edges standard way, pushed v comma color to u, pushed u comma color to v, and then took the input for source and destination, and then called this min distance function. So what is this min distance function doing? Initializing the answer with n plus 1, and then getting those dsr and ddg values, then checking for each value from 1 to n, right? That checking if we use this ith node as the transition node, that node after just after which we transit, just after we switch from red to green edges, right? So if the current node is equal to the source or destination, right? We just discussed that those cannot act as transition nodes. Or if it is not possible to reach the current node using only red edges from the source, or is it not possible, or it is not possible to reach the destination node from the current node, using only green edges, in all those cases we'll have to continue. But otherwise we can take the answer, we can take minimum of the answer with the DSR plus DTG value, and in the end if the answer's value is equal to n plus 1, then it means that there was no valid path. Otherwise, you know we have an answer. Please write something on the chat if it is clear or not. Do you want me to cover something, or is it fine? So in the meantime I just uh, iterate through this go through this BFS distance function. So so yeah, all of the other stuff is pretty standard, like we discussed in the while discussing BFS. The only difference is we have this color passed the to the BFS function, and when we are iterating through the neighbors and we are adding the unvisited neighbors of a particular node, we are only considering those edges to be the part of the graph which have the same color as the required color, right? So if the visited is true or the current color is not equal to the required color, we'll just continue and we'll just disregard that particular edge. All right. So I hope you guys liked this question and the session as well. I really thought that the question is nice when I first encountered the question. So yeah, guys, this was the today's session. So just to remind you guys, if you like the session, if you like other sessions of mine and other educators, do consider giving it a try. All right. So uh, so you can use this promo code Pulkit CP, like I told, to get the subscription for 9.99 per month. All right. So yeah, this was it from my side for today's session, guys. Thank you, Tricks. And to answer your question, Adip, yes, I did receive an interview call, but uh, yeah, like not exactly interview call. They are just sending out mails to the people with with ranks with ranks within their range to upload the resume. I have uploaded the resume. Interview call not yet. Uh, Okay, guys, great. Yeah. Uh, so I'll just sign off now. Thank you all for joining. Do consider buying the Plus platform if you like this session and other sessions that happen now and then. Okay. Thank you. Bye.